Hi, good morning everyone. I just want to say a few things about the event, so we start. First of all, let me say that we are very happy to see a lot of people here, a lot of old friends, a lot of new faces. So we make we try our best so you can have a wonderful event. And how the school works. The plenary talks are intended for everyone. For the mini courses, Rob will talk a bit about them. And during the mini courses, there will be like 3 activities happening at the same time. The mini course, and then some rooms for group work so the researchers can collaborate together. And also another room for the students which decide to attend only one course. They can use a room to solve the exercise, and there will be some TAs to assist you with that. And just more a few things. Remember, please, the official photo on Wednesday after Thibaut's talk. Today, in the end of the event, we have a cocktail, so everyone can talk and know each other better. And on Thursday, there is the talent show. So if you have any kind of talent that you consider a talent, the threshold is very low, so no worries about it. So please, talk to Marcelo Campos here. He will organize this. So on Thursday, we have 4 hours of talent show, so there will be some snacks, some water, some drinks. I mean, some people are saying that there will be some liters of beer, we'll see. But now I'll let Rob talk about the mini courses and about the hiking also on Wednesday.
Okay, just very quickly about the mini courses. There's 2 mini courses. Everyone should go to Alex's mini course this morning, but he's promised to start slowly, but he'll probably increase the pace. So the less experienced students may want to drop that. And then do the TA sessions for my course. My course will be very, very basic. Please, anyone who has seen the probabilistic method before, do not come to my course, especially not the first two classes. You can maybe come to the 3rd and 4th ones, okay? So in order to help me go as slowly as possible. People who haven't seen anything before, please come and please, please hopefully enjoy. Second thing, the hike. The hike on the afternoon will be just up the hill here into the forest. It won't be very difficult, maybe like half an hour, and then there'll be a longer version for people who are more energetic. Bring swimsuits so you can jump in the waterfalls. It'll be a lot of fun. So, cool. And right, so without further ado, I'd like to introduce our first speaker, Matthew Jenssen from King's College London, who will tell us about lower tails via Gibbs uniqueness.
Hello, is this good? Microphone working? Okay, great. Thank you so much to the organizers for inviting me to be here. It looks like a really wonderful week, and it's always lovely to have an excuse to come to this wonderful place. I'm going to talk about lower tails via Gibbs uniqueness and hypertrees. A lot of words there. Let's start with lower tails, and we'll get to the rest of it throughout the talk. So what's the type of question I'm interested in today? Here's one. What is the probability that GMP is, let's say, KR free? Okay. So by the way, if I'm talking too slow or talking too fast, writing too small, just shout. And if you have any questions, I know people are coming from different backgrounds, so just if anything's unclear, please just shout. GMP is the Erdős-Rényi binomial random graph. This is a clique on R vertices, and I'm asking what's the probability that this doesn't appear as a subgraph of my random graph? Some other types of similar questions of a similar flavor. We could ask, what is the probability that, let's say, a p-random subset of, let's say, the integers 1 up to n contains no k-term arithmetic progression, which I'll abbreviate as KAP free. Or you could ask a p-random subset of some group is sum free. Let's say of maybe Zn is sum free. So a lot of you will notice or be very familiar that these all fall within the same framework of independent sets and hypergraphs. And indeed, that's the kind of level we're working on today. But when I'm actually going to focus on this first question, and in fact, I'm just going to focus on it for a triangle, just so we can have something concrete to look at, and I can show you some results. But when I show you the proofs of the results, it'll be completely clear how we can deal with all of these questions. I should say I've written lower tails here. These are rather extreme lower tails where I'm just forbidding the structure completely. I'm saying I don't want any clique. I could be a little bit more mild and say, maybe I just have fewer copies than expected. So maybe 1% of the expected number of copies. And I've written GNP here. It's also a very natural question to ask the same question for GNM. So I'll just write same Qs for GNM, etc. So again, I'll focus on this simple scenario and maybe say a few words at the end how you can deal with this more general case where you're sort of asking for general low tails or how it adapts to GNM. OK, great. So let's think about the probability that GNP is triangle free. OK, let me just say a couple of things that are known here. So I'm going to state a theorem. This is a concatenation of results by Jenssen, Vucak, and Ruchinsky from around 88, and Vucak from 2000, that says the following. So if P is little o 1 over root n, so much, much smaller than 1 over root n, then we know the logarithmic asymptotics of this probability. So the log of the probability that G and P contains no triangle, this is asymptotically equal to minus n choose 3 p cubed. Okay, I'll come back to where this formula comes from, but let me complete the statement. Oh, and by the way, so this is the sort of level of accuracy I'm interested in today about my probabilities. I want to determine the log of probabilities up to leading order asymptotics, or determining the rate function, if you like, of this probability. So this is Jenssen, Vucak, and Ruchinsky. It's sort of the first application of Jensen's inequality that you might have seen in a probabilistic combinatorics course. The second half of the theorem is due to Vucak. It's a bit more tricky to prove. It says if P is much, much bigger than 1 over root n, then we can also determine this rate function. It's asymptotically equal to n squared over 4 log 1 minus p. So Vucak proved this using sparse regularity methods. It can now be proved a lot more simply using the hypergraph container method. So two very, very different approaches to prove these two halves of the theorem. Just briefly, where do these formulae come from? How should you think of them? So this is sort of saying, I'll just do a sort of scribble over here. Imagine sort of the appearance of triangles were all independent. So what's the probability I don't have a single triangle? It's 1 minus p cubed. And if all of these appearances were independent, then I don't see any of them with this probability. And so that's where this guy is coming from. And you should think of these as sort of coming from disordered graphs. They have no particular structure whatsoever, so maybe they look like something like this. Okay. This comes from a very different construction. This is saying, why don't you just be bipartite? Okay, so what's the probability of being bipartite? Well, let me fix a bipartition. And I just say I don't want any edges in here, and I don't want any edges in here. And that occurs if it's a balanced bipartition, n over 2, n over 2, say. And there's roughly n squared over 4 edges inside here. So, and I'm allowed edges going across. So this is where this comes from. So this is coming from a bipartite construction. It's a very sharp change in structure. OK. So you'll notice this sort of leaves a little gap, and that's sort of where I want to zoom in today in my talk and ask, what if P is in this window? Let's say it's C over root n, where C is some fixed constant. I'll call this the critical window, and I'll justify the name in a second, or in a few slides' time. But let me just mention this same gap between these two methods where sort of Jenssen-type approaches apply and hypergraph container methods apply. The same gap appears in all these questions over here. OK. And so we asked, how can we start to investigate this? What happens inside the critical window? I should say something is known about this. Jenssen inequality applies here too. What does it tell you? It says that this probability is of the order, so capital theta, so equal up to some constants, n to the 3/2. But I'm interested in this level of accuracy. What is the rate function? OK, are there any questions so far? OK, great. So let me give this constant in front of here a name for convenience. So let's suppose I've got my P is constant over root n. I'll let f of c be the limit as n tends to infinity of 1 over n to the 3/2. So Jenssen's inequality tells us this is the correct scaling of this log of the probability. So in other words, I'm just asking, what is the constant out front? What is the rate function to first order in asymptotics? So here's a result. Very, very remiss of me. I haven't mentioned my co-authors. Let me do that now. A brief interlude. So all of this is joint work with Will Perkins from Georgia Tech, Aditya Potakuchi from York University in Canada, and Michael Simkin from MIT. OK, great. So we can determine this f of c if c is small enough. So if c is less than the square root of e over 2, then I can tell you what f of c is. It's some vaguely horrible formula. I'll write it down, but then we'll discuss. And I'll draw you a graph, and things will become a lot clearer. But just for concreteness, let me tell you what it is. This is going to be the Lambert W function. So W is just the inverse of xe to the x. So that's this funny function of 2c squared to the 1/2 plus 3 w2c squared to the 3/2 over 6 root 2, of course, minus c over 2. OK. Fine. Let's plot this function. OK, let's see what this function looks like. So this is some log. I took a log of a probability, so it's negative. So let me draw my axes like this. So this is c. This is f of c. And the function looks something like this. OK. Now, observation, this function can't continue to hold for all c. Why? Because we have a nice lower bound coming from bipartite graphs. What does that look like? This holds, so this is like, when I do the right scaling, turns out to be the straight line negative c over 4. OK, so we certainly have a lower bound that looks like this. And they cross. They cross at around 4.3. OK. So that means f of c can't be an analytic function for all c. Physicists have a name for this. There must be some non-analytic point. They call it a phase transition. So phase transition does occur in this model. And we've shown that this curve is correct up to this funny constant, which is about 1.16. And I think it's a complete mystery how to fill in this picture. So I think just this very first question in random graph theory, probability GMP is triangle-free, has this really cool mystery about phase transitions at the center of it. So yeah, I think that's really nice. And I'd love to fill in this picture. I should say we can also determine this for large C. Maybe I'll say something about that. So it's not the straight line, but we have two analytic functions that are different. And of course, the simplest picture would just be to continue them both and see where they meet. Whether that's true, whether there's a unique phase transition, who knows? Okay, and similar phenomena pop up in all of these other problems as well. So I'm just going to focus on this small c range today. Okay, great. Let me tell you a little bit about lower tails now, where we just ask for fewer copies, just because it has some different interesting behavior, actually. So I think it's worth mentioning. So what do I mean by lower tails? Let me make it a little bit more precise. Let's now let, say, X be the number of triangles in GMP. Number of K3 in GMP. And let's say epsilon is between 0 and 1. I'm going to be interested in the probability that X is at most epsilon times its expectation. So up till now, we've been considering the case where epsilon is 0. And now that we're just considering this more general situation. And analogous to this f of c function, I could define for you fc epsilon to be the analogous rate function. So this limit of n to the 3/2, the log of this probability that xnp is at most epsilon times its expectation. And I won't bore you with all the results, but let me just state one of them sort of roughly. Turns out if epsilon isn't too severe, if epsilon is bigger than 1/2, so far away from 0, then there's no phase transition in this model. So if epsilon is bigger than 1/2, f of c epsilon, we have some funny formula for it, but let me just write, is analytic at all positive c. Okay, let me draw a picture for you again. Maybe I'll squeeze it here. So let me draw fc of 1/2. So I'm just asking, what's the probability GMP contains at most half of the expected number of triangles? fc 1/2 looks something like this. And there's an intuition for why there is no phase transition here, which is the following. So when c is really small, how do you get rid of triangles? Well, you can sort of just like locally delete things and just suppress your number of triangles like that. When c gets larger and larger, we saw one strategy for avoiding triangles. But there's another strategy, a third strategy, if you will. Can anyone tell me what another strategy for suppressing the number of triangles is? Exactly. Just pretend you're G and Q, where Q is less than P. Okay? And this is saying that when epsilon's not too severe, that this strategy wins out, and actually you can interpolate these two strategies in a nice analytic fashion. So this is interpolating two formula, one that's coming from a Poisson-type bound, and one which is coming from the G and Q bound, which sometimes people give the fancy name the replica symmetric bound. So this is Poisson. And this is replica symmetry. And this curve is sort of interpolating. So this is correct in the large C regime, this is correct in the small C regime, and this curve interpolates these nicely. So node phase transition. Let me just mention in one sentence a note about GNM. In GNM, this strategy, this replica symmetric strategy of suppressing, just pretending you're G and Q, that strategy is forbidden. It doesn't exist, right? You're a GNM, you have M edges. So then actually you have a phase transition for every epsilon. So I'll just write GNM. There exists phase transition no matter what epsilon is for all choices of epsilon. Because you forbid this replica symmetric strategy. Yes?
Is this half sharp?
Great question. This half is not sharp. What our proof gives is something like 0.499, some Lambert thing. But that, I don't believe, is sharp either. And yeah, it's a really cool question. What is the sort of phase transition in epsilon for when you see this phase transition to node phase transition? So for phase transition, phase transition. Yeah, what is the correct epsilon?
For epsilon smaller than that, we don't know if there is a phase transition for any other epsilon.
Yes. So I think I know. I think I can show, but that's a sort of a separate thing. But yes, if you read the paper, then we don't address this question. But yeah, for epsilon being like 0.1, I think I know how to show that there is a phase transition. Yeah. Okay. Very good. Any questions before I turn to the proofs of this, of these results? Okay, so the proof I'm going to show you is a sort of general approach to these types of questions. And they're inspired by tools in computer science and statistical physics. So I hope sort of to show you them at this combinatorics conference that hopefully you'll find it interesting and maybe even useful. And as I said, I'll show you the proof in generality because at this point it's no easier to think about triangles than anything else. And the language and the setting here, of course, is hypergraphs. Okay? So let me talk about Gibbs measures on hypergraphs. Okay, so H will be some k-uniform hypergraph. I'll have vertex set V, edge set E, k-uniform. I'll denote by curly I of H the independent sets of H. The collection of all independent sets in H. One more definition, then we'll do an example. H sub P is going to be a P random subset of the vertex set of H. P random subset. That just means I select every vertex independently with probability P. Okay, and the probabilities I'm interested in are the following. What's the probability that HP is an independent set of H? So this is the main object of study. Where does this come from? Let's do an example. So all of these questions I mentioned can be cast in this language. Let's see how this relates to triangles. So I'll define some funny hypergraph H triangle, which is the following. The vertex set will be the edge set of the complete graph. So this construction will be familiar to many, but let me still go slowly. The edge set will be, well, whenever I see three edges of Kn that form a triangle, I'll put a 3 uniform edge around them. Okay, so the edge set is, let's say, EFG, such that E, F, and G are edges of Kn form a triangle. Okay, what's the point here? The point here is that independent sets in this hypergraph are collections of edges where I don't see an edge, so I don't see any triple forming a triangle, so I'm a triangle-free graph. So the independent sets of H are natural bijection with triangle-free subgraphs of the complete graph. Okay, what is this H sub P in this example? So just continue with this example for a moment. So I'm selecting a p-random subset of V. That's me selecting a p-random subset of the edges of Kn. That's just G and P. And I'm interested in the probability that's an independent set. So I'm interested in the probability that's a triangle-free graph. So just to make it explicit, the probability that HK3, so P is an independent set of H, is just the probability that we've been discussing. GMP, triangle-free. Okay. Very good. I'm now going to put another confusing measure on the hypergraph. So just bear with me for 1 or 2 lines, and then we'll see why I did it and how these two measures connect to each other. So here's a very simple measure, p-random subset of the vertices. I'm now going to show you a slightly more confusing measure. It's as follows. So let's let lambda be greater than 0. I want you to consider a probability distribution on independent sets of H. So consider the following dist distribution on independent sets of H. I'm going to select an independent set with probability lambda to the size of the independent set. And this is just some normalizing thing that makes it a probability distribution. OK, this has a name. It's called the hardcore model on a hypergraph. And this falls within the class of Gibbs measures. And when we deal with lower tails, we do indeed have to consider some more general Gibbs measures. But this particular one is called the hardcore model. It's very well studied. What's the relevance for us? Well, let me just say one brief thing. So statistical physicists really care about this partition function and understanding this partition function and examining its properties. Why? One reason is that cool probabilistic information is hidden inside of this partition function. For example, through derivatives. Let me just give you a quick example that will be relevant to us. Suppose I wanted to understand the expected size of an independent set drawn according to this model. Let's just write out the definition. This is the sum over all independent sets in H. The probability, well, its size times the probability I selected it, lambda to the size of I over ZH. This is just lambda, the derivative of ZH over ZH. Or if you like, so I took a derivative, this I came down and multiplied by lambda to fix it. Or if you like, this is the lambda times the logarithmic derivatives. OK. So it's a nice fact that I can understand this first moment by taking some derivative of the partition function. OK, what on earth has this got to do with this guy here? Well, let's just write out the definition of this. So what's the probability? So let's just switch gears for a second and go back to this nice simple measure where I'm just taking p random subsets of H. What's the probability that's an independent set? Let me write out the definition. This is just the sum over all independent sets, the probability I selected that set. So p to the size of I, 1 minus p to the size of v minus the size of I. Okay, just writing out the definition. Let me take the 1 minus p to the v outside. This is 1 minus p to the size of v. And what I'm left with is a sum over independent sets p over 1 minus p to the size of I. That's what this partition function is. I should have written out the definition. Let me just do it now, just to make it explicit. How do I make this a probability measure? I sum over independent sets, lambda to the size of I. OK. So this is exactly the partition function here. So that's the connection. Let's take stock. OK, so I have these two identities. OK, I have this very confusing large deviation probability. The probability is, say, GMP is triangle free, but with respect to a nice chill measure. OK, what this is saying is to understand this probability, it's enough to understand this partition function. But to understand this partition function, it's enough to understand this first moment, because if I know this, I can just do some integration to recover the log of the partition function. So it seems like a cheat. Got a very confusing large deviation probability, and now we're just asked to calculate the simplest possible first moment. What's the catch? This is an extremely confusing measure. Okay? So there's some trade-off here, and it's unclear that we've won anything. But I'm here to tell you that this is a useful perspective. And one reason is computer science and statistical physics have lots of cool tools for dealing with confusing measures. Statistical physics is, in some sense, the science of analyzing confusing probability measures. And so I want to share with you one of these tools. I should say statistical physicists have tons of tools for confusing probability measures on graphs, fewer tools on hypergraphs, sometimes for good reason that the tools genuinely break down. And actually, we came up with a proof when we were first, and we even wrote a paper, that just worked for the triangle, just worked that GMP is triangle-free. And that's because we did some trick. So the triangle-free hypergraph is a 3 uniform hypergraph. But we did some trick where you look at the link and to force ourselves into a graphy situation and apply these graph tools. And it wasn't clear how to make this work in general. And somehow later, with the benefit of hindsight, we came up with the right tool that generalizes to the hypergraph setting. OK, so let me tell you that tool. Let me not tell you the proof that only works for triangles. OK. Having said all that, let me tell you the tool for graphs, and then just tell you that it works for hypergraphs as well. It'll be clear sort of vaguely how these things generalize to hypergraphs. OK. And so sort of the broad umbrella I want to talk about today is something called correlation decay, or Gibbs uniqueness. Sort of two sides of the same coin, if I define things properly. OK. So again, let's just focus on graphs. Let's focus on hardcore model. Remember, that's our confusing measure we're trying to understand. The hardcore model on graphs. So suppose I'm in the following situation. I have some graph. Maybe it looks like this. Some graph H. A, B, C, D. OK? And I want to understand the marginal at A, just the probability that A is in my independent set with respect to the hardcore measure. So there's a really neat trick for doing this. And this is a theorem of White's. From around 2006. That says that this probability is equal to some cool construction, which I'll now show you and then fill in what the theorem is. So he tells you how to compute this in a really neat way. Yeah, and I'm very happy to show this to the combinatorics group, because I'm not sure it's such a well-known tool, but I think it could be very useful. So what you do is you build something called the tree of self-avoiding walks. It'll be evident when I draw the picture what I mean by that, rather than giving a definition. So here's a self-avoiding walk. A, B, C, D. Okay? Another one is A, B, AC, let's say D, or ACB. Okay. I'm actually also going to record when I close the cycle. Okay, so I'm going to ACBA and ABCA. Okay, that's the only slight twist. I'm just going to record why I stopped when I close the cycle. And if I did close a cycle, I'm going to do something slightly strange. I'm going to put what's called a boundary condition on that vertex. I'll explain what I mean in a second, but I'm going to force this one to be occupied and this one to be unoccupied. That just means if I consider independent sets on this graph, I'll force this one to be in and this one to be out. Why did I do this one unoccupied and occupied? It just depends on which way around the cycle I closed it. Okay? The exact construction isn't so important for today, but it is very simple. So this gives us some tree, importantly. The important thing is this is a tree. I'll call it TH of A. Okay, and the theorem says that this marginal here is the same as the marginal of the root of this tree, once I take these boundary conditions into account. So I'll write the root is an I. If you don't like to think about boundary conditions, just A being out just means you can just delete that vertex if you like. A being in means it's an independent set, so I better kill all its neighbors. So just get some new tree. And that's what I plug in here, if you don't like thinking about boundary conditions. OK. But the key fact is here, I've now reduced this to a computation on trees, and trees are much easier to deal with than general graphs. They have this nice recursive structure, and everything becomes easier on trees. So this is wonderful. And the simplest kind of possible tree in this context is a nice regular tree. So this is maybe one of several reasons why physicists like the following object, the delta regular tree. So this is a 3 regular tree. In general, I'll just note it dt delta, and I want you to think of this as an infinite tree. And we want to study the hardcore model on this object. And what physicists are interested in is, given lambda, does this model display long-range correlations or not? What do I mean by that? So suppose I just truncate this tree at some depth L. Okay? And then I just impose some boundary conditions at the leaves. Can that affect the probability that the root is in the independent set? Okay? As I want you to think of L getting larger as the boundary recedes. If yes, we say there's long-range order. And if it doesn't affect, we'll say there's correlation decay. Okay? So we're interested in when there's some correlation decay, meaning if this is the true value of the probability of the root being in, then if I just truncate at depth L, then I only affect this up to some 1 plus little o1 as L tends to infinity. So here's a folklore theorem. About decay of correlations. Theorem, folklore. If lambda is small, smaller than some lambda critical, which is about E over delta, then the hardcore model on TD, T delta, exhibits decay of correlations in the sense that I kind of waved my hands about over there. Decay of correlations. Very good. How much time do I have? 5 or? At least 10 minutes. Oh, great. 10's perfect. OK. Brilliant. OK, good. So then I can tell you sort of a little bit more background. So Weitz was interested in this from a computer science perspective. Why? So he was interested in the problem of, can you sample from the hardcore model efficiently? And actually, we've got this lambda critical. I should tell you that when lambda is bigger than lambda critical, there is no decay of correlations. Okay, maybe you inferred that yourself, but okay. So this is the correct phase transition on the tree, at least. Okay, so Weitz was interested in, from a computer science perspective. He wanted to know, if I give you a graph and some lambda, can you efficiently sample from the hardcore model, approximately? This is actually one of the earliest problems in computer science. So this is what people were up to on these maniac computers in the 50s. This is what the Metropolis algorithm was invented for, was essentially to sample from the hardcore model. Actually, it's a continuous version, the hard disk model. So Metropolis algorithm, sort of the early instance of the Monte Carlo Markov chain method. And it was voted one of the 10 most influential algorithms of the 20th century by Rutgers or something. Okay, so this has a very prominent history, this problem in computer science. And Weitz gave a really cool way of sampling from the hardcore model. So it turns out if you want to sample from the hardcore model, approximately it's enough to estimate the marginal at any vertex, okay, very accurately. And so he built this tree, and then it says, okay, I now just need to estimate the marginal at the root of this tree. But when lambda is less than lambda critical, I have this nice decay of correlation property, so I can just chop this tree. In general, this tree can be quite large, right? If you draw out the whole tree, if my graph has n vertices, it could have depth n. So I don't want to look at the whole tree. I'm just going to truncate it at some depth. And then I can just brute force on that tree. And this gives an efficient way of approximating marginals. I should say Weitz needed a slightly stronger version of decay of correlations called strong spatial mixing. This is weak spatial mixing. But that's the general idea. So this is a really influential theorem in CS. And what's really cool is, so that gives you a nice algorithm for sampling below lambda critical. If lambda is above lambda critical, there is no algorithm in general for sampling from the hardcore model. This is a famous result of, unless NP equals RP, this is a famous result of Alan Sly. OK, great. And what's this funny Gibbs uniqueness that I wrote down? So it turns out this is equivalent to saying that there's a unique Gibbs measure, a unique hardcore measure on the infinite tree. Because I drew this infinite tree, it's not clear how to define a measure on the independent sets of an infinite tree. And so Gibbs measures are a nice way of generalizing these finite measures and finite graphs to infinite graphs. But when you write down the definition, it's sort of unclear whether the measure is unique or not. And this is actually one central consideration of statistical physics is whether, given a model and a graph, there's a unique Gibbs measure or multiple. So when you go from uniqueness to coexistence, this is another way of discussing phase transitions. So this is equivalent to saying that there's a unique hardcore model when lambda is small on the infinite tree. But somehow this decay of correlation is a bit more intuitive to talk about, at least. OK, so it turns out you can do this for hypergraphs as well. So you've got the hardcore model on a hypergraph. You want to know the marginal at a vertex. You build a self-avoiding tree of self-avoiding walks, what I won't quite define. And the marginal at the root is, this theorem still holds once you define things correctly for hypergraphs, it turns out. And people actually knew about this already, so we didn't invent this. It's come up in a couple of different contexts in CS and study of zeros of partition functions. OK, so let me just write Yes, there's a hypergraph analog here. So that's really nice, because remember, we were interested in the expected size of an independent set. So it'd be really nice if I can understand a marginal or a vertex, because I just sum them up. That's the expected size, right? So really what I'm interested in are these marginals. So all I'm going to do is I'm going to take my hypergraph, build this tree, and try and see if I can figure out what the marginal of the root is. Okay, that's all I'm going to do. Okay, and I only need to do this. Okay, so I give you a hypergraph, and you try and build this tree. What on earth does this tree look like? Okay, it'd be really nice if I could say something about its structure. I only need to control the structure up to constant depth, arbitrary constant depth. Remember, because I'm interested in just understanding this marginal up to 1 plus little o1. So long as I can keep control of what this tree looks like to constant depth, depth 1 million, arbitrary constant, then I'm happy. Now, what makes this tree construction confusing is if I close lots of cycles and I'm putting in boundary conditions everywhere, then things are confusing. So I like trees that don't have, I like graphs which maybe don't have too many cycles, so I'm going to call them tree-like, and similarly for hypergraphs. So let me tell you what a tree-like hypergraph is. Okay. Let me go here. This is a sort of new title, tree-like hypergraphs. And this is my final slide, as it were. So I'm going to write down a bunch of conditions on the hypergraph that basically mean this tree, this white tree, looks nice. And then some of the definitions will look very familiar. So just a quick definition. I'm going to write delta L of my hypergraph, the L degree, to be the maximum number of edges that a subset of L, subset of size L can live in. So the maximum number of edges such that E contains this. So take an L subset of the vertices. How many edges can that live in? That's my maximum L degree. H, again, is VE. It's going to be K uniform. Okay. So we'll say a tree, say a hypergraph, say H is tree-like. Maybe it's not the best name, it's a work in progress. So tree-like, if it satisfies the following conditions. These L degrees are controlled, meaning the L degree is little o of the 1 degree, which I'll just denote by delta, the max degree of my graph, to the power of k minus L over k minus 1 for L between 2 and k minus 1. So my L degrees aren't too large. And we need one more condition, which I'll just draw a picture for. If I give you 2 vertices u and v, the number of k minus 1 tuples that complete them both to an edge is little o of delta. So this is some notion of co-degree. So k minus, let me write little o of delta of these. So these conditions have come up in several other places in the combinatorics literature. This is sort of precisely the type of thing you need to get the hypergraph container method off of the ground. And that's really nice because here we're sort of working with these models in the disordered phase. If you want to study them in the ordered phase, when lambda is large, the first step, the hypergraph container method, is a really cool first step. So these things fit together really nicely. These have also come up. You might have seen these conditions in the work of Bennett and Bowman, where they were studying random greedy independent sets in a hypergraph. And they were saying if you have conditions like this, then we can say how long this process runs. Process is like the triangle-free process. And so actually, in a way of reinterpreting the Bennett-Bowman result is to say, if my graph is tree-like, then the terminating density of the random greedy process is the same as the terminating density on just the tree. So they don't phrase it that way, but that's a sort of justification for this tree-like name. Okay. So what's the point of this? The point is, so just to conclude, let me leave this up here, actually. The point is, say, let's suppose for simplicity that if H is delta regular, let's just say, and tree-like, then this TH, then for any V, and for all V in the vertex set, this White's hypertree, THV, is close to just a regular K-uniform linear hypertree, to a delta regular K-uniform linear hypertree. So that's how I can, that's sort of the nicest possible situation where I can really just, the simplest possible tree you can hope for in this setting. So maybe I'll try and draw a part of a 2 regular 3 uniform hypertree. Maybe I'll denote this by T delta 3 for 3 uniform. So if the white tree looks like this, then I can write down, for example, let me write H for this, just to take a concrete example, HK3, this triangle hypergraph. I'm interested in the marginal, so V is in my independent set. This is telling me that it's enough just to look at this tree. And it turns out I can just calculate this directly, but rather than write down the confusing formula for what it is, let me actually tell you in the last 1 minute the heuristic that all of this is making rigorous. Okay, so here's a heuristic for what this marginal should be. So remember, I'm doing this p-random subset of this triangle hypergraph. That's just some distribution on triangle-free graphs. So let's try and figure out, let me call this Q for density. Let's try and figure out what this Q should be. So here's a little edge in my Kn now. So this is a vertex of the hypergraph. Let me figure out what the probability that it's in. Well, it better not have a P2 sitting on top of it, because then it couldn't be in, right? It's blocked. Remember, I don't want triangles. What's the probability of this being unblocked if I'm just being a physicist? It's just, well, these should all be Q as well, and they should all be independent, so this should be like 1 minus Q squared for not having this P2 to the power of, n minus 2 for not having any of them, pretending they're independent. And then you say, okay, now I'm nice and free and available. Now, if I put myself in, I kind of pick up this factor of lambda. Lambda for being in over 1 plus lambda, 1 for being out. Okay? So this is just a heuristic for what this probability should be. But this was a heuristic for what Q is, so this should be Q, right? So we have this fixed point equation for Q. And if you rearrange, this means Q is the square root of W2 lambda squared n over 2n. And that, by no coincidence, is the correct value for this root occupation. So this heuristic is what this statement is making rigorous. And this is where this funny lambda W function comes from. And so if you just integrate this, that's where this horrible formula I showed you at the beginning of the talk comes from. So it's actually fairly easy to motivate. OK, I'll stop there. Yeah.